Swayam Prabha. Digital India. Educated India.
So, moving towards the systems view, okay, I need to change slide. So, we have goals, based on the goals take decisions that influence state of system. That all again, it is just a kind curved diagram of the same linear diagram we saw a couple of minutes, a few minutes ago. This alone is not enough, we do not have abstract goals, the goals are always relative to the state of the system. So, based on the state and based on that and the goals and based on the gaps, we take the decisions. But as soon as we take decisions, that is going to affect the state of the system, which will force us to make more decisions in future. And whatever decisions that we take will have effects. Sometimes we call it side effects because we are not planned for it, we are not thought of it, we are not anticipated it. Maybe we were just, we did not know, or maybe we were just ignorant, or maybe we were just too lazy, saying that if you are considering all that will make my life more difficult, so let me just ignore all that. It could be any of the reason, but whatever it is, you took a decision, it will have effects. Sometimes you call it side effects, but it still affects. Unfortunately, you are not the only player in the system. So, state of system also affects the action of others, and others have goals. The simple example is even registering for a course. It is not that only you are going to register for a course, and if course has a limit and you told your friend that I am going to register for this course, suddenly you find that your entire batch is registered for the same course, and before you could do it, limit has hit. Probably it was your idea to do that course in the first place, but it is already exhausted. So, your goal is unmet, and they will also have more side effects. This is what, so as we move to systems view, it is not that for every problem we need to go and model the entire world. We need to look at what are things that can influence, that can affect, and if it is too much, and learn to draw a boundary for the system and consider as much elements as required to address the issue in a little more fundamental manner. So, how to do systems thinking? First, we are going to learn this act of thinking dynamically. The course is called system dynamics. So, we have to do, and dynamics means behavior over time, how things are evolving over time. We are familiar with the concept, we are familiar with events. One thing that we are not familiar is, as soon as a problem is presented, we should say, okay, what is happening over time? If I say, okay, there is a unemployment is at 8%, okay, that is fine. Let me see how is unemployment has been behaving over the last 10 years, 15 years, 20 years, and how do you think it should behave in the future. So, let us try to understand what kind of dynamics that we want to create, because it is not a one time thing, it is over time. Whatever decisions you are going to make is going to have an impact over time, and there is a lot to learn from what is happening in the past. So, we are going to cultivate this thinking dynamic in the terms of dynamics of various variables. Second is causal thinking, thinking in terms of effect, cause and effects. We are going to identify some variables and see whether that has an effect on something else or does it cause some other effect. Identify is there any potential feedbacks within the system, what are the delays that is happening in the system. So, we can start explicitly identifying them. Once we are there, then we will also learn how to do what we call as stock and flow modeling, where we start to think of things as accumulations. So, whatever we, what can I say, like even if I stop, say to reduce say the total pollution within the lake of Powai, I can say, okay, let me ensure that no sewage water enters the lake. But already there is so much sewage water already entered the lake, already so many pollution has already entered the lake, right. So, that has accumulated over the years. Just because you turned off the sewage today doesn't mean that is going to disappear. So that becomes more apparent as we start looking at things as accumulations. It is getting accumulated somewhere, and there has to be mass balance. We are used to mass balance in a more compact setting, but that is true for environmental systems also, social systems also. There is already a accumulation of things. It can be physical, like pollution level, or it can be even what can I say, mental models or beliefs. Over time, people have been led to believe some things. You can't just send one news article or one announcement saying that from today you have to do like this. You can't change people's belief system so immediately. People's beliefs accumulate over time. So only it will take time to change that belief and replace it with some other whatever belief, right or wrong. So that is what we mean by stock and flows. There is a stock of things. And finally, thinking endogenously, systems as a cause. We are used to attributing various things as an external factor. It is not my fault, things are beyond my control, it is because the competitor did it, it is because somebody else did it. So once you start blaming others, then you don't have any leverage. If I want to control and if I want to run it, effective operation or make good decisions, then you have to ensure that all the variables are endogenous to the system. If you say demand is external, then demand is external. Then how it happens, why it happens, you don't know. But when I say endogenous is okay, can I do some pricing schemes which will influence demand? That also you might have thought, yes, when you do pricing, demand will get affected. So now suddenly demand is not anymore exogenous, it is endogenous to a system because it is reacting to some decisions that you are taking which is in your control. So we try to look at it endogenous. Yeah, that has to be clearly characterized and left. So we have to understand that okay, these are external and these are endogenous. Yeah. So it is like this, in reality things can actually be affected externally as well as endogenously. But we believe that some are it is not affected endogenously or not are only affected endogenously or exogenously, right. So if it is indeed endogenous, then we need to identify it, and later we found that no, it is not endogenous, then we leave it, okay, it is indeed exogenous. We will do more. These characterize system dynamics approach. Just to give a brief example, when I say dynamics, this is what I mean. We look at the behavior over time. This is from the tradingeconomics.com on India's car production in the last 10 years. You can see there has been a kind of a, not a steep but a steady growth, and also you can observe cycles. You can observe standard cycles of same sizes which can use to anticipate. So if you are the manager in charge of whatever, the last quarter sale is going to dip, you better bounce back, right. So now with that will give some revelations of what has been happening for us to improve. This example of a simple causal loop diagram of this example on rat population. We are looking at the rat population is affected by the birth rate and it is affected by the death rate also. Population also affects it and affects the birth rate also affects the population. And in this example, the population also affects the, of course, the density, given that the area here is assumed to be external, meaning you don't have any control. Rats cannot migrate, they are fixed in that area. So here this is the example of an exogenous variable, and here it is assumed density influences your mortality, which affects your birth rate. These kind of diagrams are helpful to understand what are the variables in system, how they are linked to each other. There are no equations in this model as of now. As we move on, this is what is called a stock flow model, where these rectangles are called as stocks. They accumulate things over time and they are affected by the flows shown by this thick arrows with a valve infection rate. So, there is a susceptible population who get infected with some disease, they can become infected population who after they recover become recovered population. So, in this diagram the total population is conserved. The population, suppose they start with whatever 100 people, either they have to be susceptible, at some point if they get infected, so 10 people get infected, this becomes 90 and this becomes 10, and when they start recovering, suppose 2 people recovered, this becomes 8 and this becomes 2. So, that total people gets conserved, they do not just disappear from the system, right. So, there is conservation of mass. So, when we move to this, we will be moving to equations relating them. It need not be simple addition, it can be whatever type of relation that is requires between the various variables. Since all our engineers, the underlying equations are all differential equations. So, we can nicely model it once you have the equations, and if it happens to be linear models, various linear systems theories can be applied, and whatever methods we learn to analyze differential equations can be adopted here to understand and solve. But in all the other courses you would have learned only with x, y and z and various Greek alphabets and Roman numerals, I mean Roman letters x, y, z and differentiation, double differentiation, all those things. The difficult and challenging part is identifying with the variables, contact rate, total population, infectivity, what are all those things, and then coming up with the equations, and then once you have the structure and find it linear, then we can solve it. If it is non-linear, then we resort to a lot of simulations to understand the dynamics. So, we will be restricting ourselves to simulations, and towards the end we will be looking at some specific scenarios. We can look at what kind of control theory approaches can be used. So, system dynamic methodology is modeling technique to frame, understand, discuss complex issues and problems. We are going to be focused on behavioral system, we are going to look at system boundaries, interrelationships, learn from the model development process itself. So, that is the biggest learning also that you will get. Till now, given a problem we can solve. Part of the exercise and learning in this course is how do you figure out and understand and draw the boundaries of all the problem. How do you identify the variables? How do you identify relationships between them? Once you have that causal map, that itself is a big learning. Till now nobody has shown the links and has tried to understand what affects what. So, even coming up with that itself is a learning process. It is not that it has to be simulated, just coming with causal map and then building the simulation and then trying to analyze. So, taking any physical or economic or social environment phenomena, we will try to apply systematic methodology, so we can build some models out of it, appropriate models, and further our understanding. So, in our course we are going to learn causal loop diagram and stock flow diagrams. We are going to elicit mental models of business, social, economic, environmental systems, explicitly accounting for feedback and delays, test and improve the model using computer simulation, analyze the model and simulation results correctly. It is not enough to just build the model, we need to actually analyze it. So, this is a very popular book by Sterman, Business Dynamics. We will be following though the title says Business Dynamics, it has a lot of models on environment and social systems also. It is a big fat book. Kirkwood has put up some nice notes on system dynamics online, it is free, you can take a look at that. And basic concepts are quite easy. The challenge is when we try to apply those basic concepts in actually trying to build a model of a system that we are studying, that is challenging. Other reading material provide, I will give links to appropriate notes or whatever I write or whatever slides we put, it will be up. We will be using Vensum and maybe some Python and R if simulations become large. Maybe towards the end of the course I will teach for large models how do you do better analysis. So, we will be using computers.